Okay, Assalamualaikum and good afternoon to all my students of MEC281 Material Science. Okay, so this is the video of subchapter 2 phase diagram and part 2 because we have already learned about isomorphous phase diagram in the part 1 video in the latest video before this. Okay, so right now we are going to learn about the binary eutectic phase diagram. Okay, in the last video we have isomorphous phase diagram. So for this video we have to learn eutectic phase diagram in the no solid solutions. Okay, what is the no solid solution? Okay, we go back to the last video that we have discussed this before. You can revise back. Okay, we have three types of binary phase diagram as shown here: complete solid solution, no solid solution, and limited solid solution. So for now we focus on the eutectic for the no solid solutions. Okay guys, okay, so let's get started. Eutectic, this is kind of a new term. You never have this term before, I think. So the eutectic is the composition of a mixture that has the lowest melting point where the phases simultaneously crystallize from molten solution at this temperature. Okay, so that is the point where liquid are simultaneously converted into solid. Okay, crystallize. So yeah, you can read from this that it is from the Greek language eutectos, meaning that easily melted. Okay, so the no solid solution where the components are completely soluble in the liquid states but complete insoluble in the solid state. So during the liquid solutions here, so they are mixed soluble completely. So there is no A and B here because it mixes perfectly. But when it convert into the solid here, we have complete insoluble in the solid state. So that's why we have two types of element here, solid A and solid B separately. So where is the eutectic phase point? This one. Okay, at E here. So there is the eutectic point. Okay, so in this slide shows that region above line CED. Where is CED? Okay, I change my pen first. Okay, C to ED, this one is the liquidus. Okay, we have discussed before the liquidus is the borderline between the liquid and to the intermediate phase here, where we have L plus B and the L plus A here. So this is liquidus line. And for C, F, E, G and D, so all of these lines is the solidus line. What is the solidus? Okay, this one is the solidus. Solidus is the borderline, okay, where it is completely solid. Okay, and then region below line FEG, that here, okay, I use this color. In this region, as stated here, that is the phase of solid, and for this binary phase eutectic phase diagram, we have two types of solid. So we have solid A and solid B. So here it exists in completely solid and insoluble, cannot be mixed. Okay, so region below line FEG, right? Okay, this is one that that we have discussed. Solid A and solid B, completely separated and solid. And at point E, this is the eutectic point. Okay. Okay, so this is the example of an eutectic phase diagram. Okay, how to determine phase and phase composition. Okay, it is very similar to the isomorphous phase diagram that we have learned in the previous video. Okay, so this is the equation. You can memorize, but I think the better way is you have to memorize this value minus this value, and of this value, yeah, at Q here, minus the P value over Q value minus this one R value. So never mind, we will show you in this video after this, okay, how to find the weight fraction of solid and liquid. Okay, so this is the example of the eutectic phase diagram. And the other thing that you maybe found it is strange is the definition and the term of hyper-eutectic and hypo-eutectic here. Okay, in this slide shows that hyper is on the right side, where it is divided by the zone, okay, through eutectic point, okay, as shown in this blue dot line here. And on the left side, there is we call hypo-eutectic. Okay, so here is L plus B, L plus solid B, and this one is L plus this one is L solid A, and this one is L plus solid B. Okay, the eutectic reaction, okay, from the liquid, okay, reversible reaction to produce solid A plus B. So these reversible reactions, you can convert back solid A and B to the liquid form, and vice versa, from the liquid form to the A plus B solid form. Okay, so let's go deeper about the hypo and hyper eutectic. Okay, so this is the microstructure eutectic diagram, lamellar eutectic structure here. So the red zone here represented by the alpha, solid alpha, and then the blue one is the solid beta. So this one is the lamellar eutectic structure. Okay, but we know we have two types of eutectic in this diagram, right? So on the left side is hypo and the right side is hyper. So the structure, microstructure of the solid A and solid B found here is quite different. Okay, what is the difference between them? Hypoeutectic, okay, placed on the left. Hypereutectic placed on the right of the eutectic point. Okay, first solid to form is the primary alpha. Okay, because the alpha is dominant here. This is alpha, this is beta. So alpha on the left side, hypoeutectic, it is dominant. So the primary alpha, first solid to form is the primary alpha, also known as proeutectic alpha. So the structure is similar, but the type of alloy in that region is different. Okay, depends on whether it is hypo or hypereutectic alloy. Okay, so on the left side, we know it is alpha region, primary alpha. So this one, the white region here, is alpha, and the beta is minor here. Okay, and it is opposite when we look at hypereutectic alloy on the right side, because okay, let's go back again, because on the hypereutectic on the right side here we have beta more dominant, so that's why the proeutectic for the hyper is beta, primary beta. Okay, proeutectic, or we call it primary beta. Okay, so it is reversible. This one you just change to beta, and this one change to alpha, and this one change to beta. Okay, so let's go to the cooling curve at eutectic alloy. Okay, if we find the temperature curve along the line at eutectic composition there, you will get a cooling curve similar to the isomorphous phase diagram as we learned in the previous video. Okay, same as single component pure metal. Okay, but if we cool down along the hypoeutectic or hypereutectic, hypo or hyper, this one is typo here, this is hyper eutectic region, so you will get a different cooling curve. Okay, instead of we have just a horizontal line here in the pure metal, now we have the curve here. Okay, because of why? Because of once the liquid reach temperature, eutectic temperature, TE, symbol TE here, it will have the eutectic composition and will freeze at that temperature to form solid eutectic mixture of two phases. Quite complicated, right? Okay. Okay, never mind. Okay, from high temperature here, okay, we cool down. Yes, we have this line until you reach the eutectic form here, and then okay, I try to put here. Let's say in the hyper region. Okay, from here, this one, and this one, this one, this one, 2. Okay, this one 3 is the TE line. Yes, the temperature line here. This is 3, and then 4 is anywhere around this region. Okay, so why it found the curve line here? Because in point 2, at that point 2, we have two phases, liquid and solid B, right? So that's why you have this curve. Okay, until it reach point 3. Okay, this is the temperature, eutectic temperature, or on that line is also known solidus line. Okay, and then we cool down more until you reach point 4 here. So this is where you have only solid. Okay, so let's try this exercise for the eutectic phase diagram. Okay, for an alloy containing 40% of B, this one B, and 60% of A. So this value shows the percentage of B, so we take it 40%, so around this one. Okay, determine the phase present, phase composition, and weight fraction of phases. Okay, three things that you have to show that in your answer. At a temperature slightly above eutectic temperature. Where is the eutectic temperature? This one, this line. So this is the TE. So we have to find information just slightly above the temperature of eutectic, maybe around here. Okay, so we know this one on the L plus B region. This is the hyper-eutectic region, hyper-eutectic, and the phase present here is liquid plus B, beta, solid, alpha. So this is the answer for the phase present. And for the phase composition, we have to find the Cl, liquid composition, and solid composition, right? Okay, so Cl here, okay, where the value of composition CO is 40%, right? And then Cl at 80.6, just below 20 here. And then how to find the composition? Weight fraction. Weight fraction, you have to use the equations given in the slide, and also similar to the equation that we have done in the previous video. So to find the weight fraction of liquid more on the left, so you have to 100 this value minus 40 this one, that value, that our CO, okay, over still 100 until it reach the liquid here, where it is the eutectic point. The composition at that point is 18.6. Okay, times 100. So that is your value. So this is the liquid. And how to find the beta, WB? So WB is just 1 minus WL, or vice versa, WL equal to 1 minus WB. So you just have to find either 1 and then 1 minus that value. Okay, so you have to try by your own. Okay, And then we go to the next example. Still containing 40% beta and 60% alpha, still on that same composition. Determine the phase present, phase composition, and weight fraction of phases at 300 degrees C. Okay, so 300 degrees C now around here. So this is the point. Okay, so where it is situated right now, the point is on the solid alpha plus beta region, right? So just put your answer in this form. Phase present is alpha plus beta. And what is the phase composition? Okay, so right now we know it is complete solid, and for the right side is the beta value, and for the left side is alpha value, or in this case is B and A. So at this point, beta B is 40%. Okay, right? And alpha here, 100 minus 40% is 60%. So if you still want to calculate, okay, let's try to calculate. CA here at this point is 0, and this one is 100, right? So our point here is 40. So 100 minus 40, CA is CB minus CO over CB minus CA. Okay, so CB. So 100 minus 0, minus 40 over 100 minus 0. So you will get 60%. Just what we found in this value, right? And the WB is 1 minus 60. 100 minus 60 is 40. So that's it. That is the answer for the weight fraction of this example. Okay, so let's try another example here. For an alloy containing 40% B and 60% A. Okay, so this one still the same point. Sketch and label the microstructure at a temperature slightly above. Okay, one point here, and another one is at 300 degrees Celsius. So the point 2 is here. Okay, so to draw the microstructure, we have to know the phase present at that location, at that point. So at point 1 is on the liquid end, B solid. So this is what we draw for the phase in LB region, L plus B. This one we have already learned in the previous subchapter here, right? During the liquid and solid region, this is kind of the draw that you must do. Okay, this one. Okay, so we know this is the liquid and beta. Just draw like that. This is the structure itself. So this is liquid L. So you have crystal solid start to form. So this is B. Okay, just like that for the point 1. Point 1 here, right? Just above the eutectic temperature. Okay, so how about the second point? Okay, second point is on the A plus B region. Only solid found is this region. Okay, so this is kind of microstructure, normal microstructure that you have to draw in this region, in this solid form. So just draw like that. It should be the circle, and then you have the pro-eutectic, and then you have the structure. Okay. Okay, but the tricky one that you have to put in your mind when you draw this microstructure, you have to know either it is on the hyper or hypoeutectic. So this kan, this is hyper, this is hypo. Why we have to know it is hyper or hypo? Because the proeutectic here, and for this point at 2, it is on the hyper region. Yep, hyper. So the proeutectic is the B, not A. So you have to put the name here, proeutectic B. Okay, that's it. And the other one, okay, this one is eutectic A, and this one is eutectic B. Okay. Okay, looks simple, but if you do not learn and you do not try by your own, it maybe looks very complicated. Okay, once you understand how to read or how to look at the phase diagram, and normally the steps and procedures is almost the same. Okay, so I think that's all for this video. We have covered the eutectic phase diagram in no solid solutions, and this video will continue with the next video for the binary eutectic phase diagram, but in the limited solid solutions. Okay, so till the next video, take care yourself, selamat hari raya, and bye bye.